Okay, but even from like the dawn of time, like trigonometry has existed. It's just we didn't really know about it. We didn't like understand why it was so important. But like even in something like the Vitruvian Man, where you see from Leonardo da Vinci, you see this connection starting to be drawn between circles and triangles. Like you can see the like triangle part of his arm right here. And then it's somehow creating this angle that maybe has something to do with the circle. But really, it's like anytime you have anything that just goes in a diagonal direction at all, that is trigonometry. Because of being able to break this is a vector. You can break it down into its vertical and horizontal components, and there you have a triangle. Wow. Okay, so in this lesson, we're going to talk about like quick review of the trigonometric ratios, introduce the idea of like radians and unit circles, talk about how this relates to geometry and algebra, which is like why I love this subject so much, because it's like when all the math you learn in high school like all gets put together into one space. And also real world connections, like where do we use this stuff in the real world? So first, just looking at a triangle and a quick review of the trigonometric ratios here. When you have a triangle, obviously a triangle has angles, and we use the sine theta to just represent like this is the angle we care about looking at. Because if you had this angle opened to a different amount, it would create a completely different triangle. Or if it was opened smaller, you would have a much skinnier triangle. And when we use this, we end up having to use ratios because obviously you can have triangles that have the same angle, but have different side lengths. So this would like have a similar angle, and these would be similar triangles, but obviously one is much smaller than the other. So instead of looking at actually what this side is, we look at how this side is compared to another side. That way, even if we had a smaller triangle, even though the side lengths themselves are different, the relationship between two of the sides is still the same. That's why we use ratios, so that we can do an angle and then we can compare any sides. So, quick review here. When we have this triangle and we have an angle, we label these sides just by their names here. Let me get that. So we're going to label this side the opposite side because it's opposite from our angle. We're going to label this side the adjacent side because it's adjacent to our angle. It's like right next to it. And it is, while there are two angles that are adjacent here, the longest side we always call the hypotenuse. Yay. It's like so familiar. It's like, oh my God, I learned about this in high school. It's all coming back to me. Now, when we combine these guys, that's when we get those ratios. So when we have sine of an angle combines the opposite and the hypotenuse. Cosine, C-O-S, combines the adjacent and the hypotenuse. And then there's tangent, and that combines the opposite and the adjacent. Whoops, I messed this up. I should have said 10% of the angle. Okay, there we go. So each of these, we have three of them because obviously there's three combinations of sides you can have. You can have this one and this one, this one and this one, and then this one and this one. So there's three different combinations of sides you can have. Technically, there are six because you could also do the opposite of all of these. You could do hypotenuse over opposite, hypotenuse over adjacent, adjacent over opposite, but that gets into the arc trig functions, and I'm not going to talk about those just yet. Okay, so these trig functions actually can be used in what we call a unit circle. So this is that connection, that like the Vitruvian Man was starting to give this idea to that, like Leonardo da Vinci was starting to like grasp a little bit, but he didn't go all the way. So the idea of the unit circle is that let's just take a circle, okay? We're going to put it on a coordinate plane, and we're going to say that this point in the middle is 0, 0. And we're going to make the radius of the circle 1. It's just a completely arbitrary number, but we're going to use 1 because it's easy to do all the math with. So the radius here is 1, so this distance here is 1, which means, therefore, that this point here is 1, 0, and then this point back here would be negative 1, 0. Going up, we would have 0, 1, and to the bottom, we would have 0, negative 1. So basically, in every distance, it's a circle. Every point on the circle is the same distance from the center. It's all 1 away from the center. However, what we can do now is we can make a triangle, because I can draw a line like this, and this is still 1. And if I take the point that we have here and I draw a straight line down, boom, we got a triangle. And depending on the angle we have, we're going to get different measures to these sides. So with this one, let's say this is 45 degrees, and I'll talk about radians as well, because radians is very useful. But let's say this is 45 degrees. So with 45 degrees, we would end up having these two sides be the same. And I'll show the algebra for finding the exact amount later. You can also take, like, basically, the idea here is you can take any radius here. These radiuses will all be 1. And if you draw your lines down, you get like a bunch of different triangles. And no matter what, the hypotenuse of these triangles, the longest side of these triangles, is the radius of the circle. So a circle you can also think of as just a bunch of triangles spiraling around to generate the circle. Okay, before we go on though, let's talk about radians. So another thing that you might have or might not have considered is, why the heck do we say there's 360 degrees in a circle? Because if you think about it, that's kind of a weird number. Why is it 360? And the answer is it's completely arbitrary. We really use 360 because it's easy to divide. You can divide it by 2, you can divide it by 3, 4, 5, 6, 8, 10, 12. It's just really easy to divide. There's no other reason why it has to be 360. So instead of counting it by 360, there's another way to count angles. And that is actually just by using the circle's geometry itself. You always start over here, and we say this is 0. And we use the equation for the circumference of a circle. The circumference of a circle is 2 pi times the radius. And with this circle, our radius is 1. So in other words, it's 2 pi times 1, which we'll just say 2 pi, which is about 6.28, but we can just leave it as pi. We can just count in pi's. So that means if I went all the way around this circle, so if I went all the way around and got back to the where I started, that would be 2 pi. Oh, but 2 pi. Which then means that if I go halfway around, then I'll have regular pi, just 1 pi. And then half of that would be 1/2 pi, which we write as pi over 2. And then from here to here, halfway between pi and 2 pi, we would have 3 pi over 2. And this is how we count angles with radians. These are known as radians. And it's called that because it's literally based on the radius of the circle. This is very useful because now it's not an arbitrary number. It's literally based on the geometry of the circle itself. Alrighty. So let's tie this now. Here's half of that unit circle. Let's tie this with algebra and geometry all together here. because it's really freaking beautiful how everything works out. So we talked about the trig functions. We talked about the unit circle. Let's put it together. Okay. So like I said, we can take this and we can create a triangle here by connecting two of these points. Whoops. Let's make that a little straighter. And this is 0. Here's pi. Here's pi over 2 at the top. And this is between 0 and pi over 2, so it's half of that. So it's pi over 4. In other words, in like degrees, this would be 45 degrees. And I draw a line straight down, and this creates a triangle. Now, using algebra, we can actually find out how big the sides of this triangle are. So the radius of this is 1. And we know that since it's 45 degrees here, it's also 45 degrees here, which means these two sides are the same length. So what we can do is we can say, using the good old Pythagorean theorem, a squared plus b squared equals c squared, we can say, well, this is a, this is b, but they're the same thing. So in other words, it's like a squared plus a squared equals c squared, which means 2a squared equals c squared. Not only that, we know what c is. We know that the radius, the hypotenuse of this is 1. The radius of the circle is the hypotenuse of the triangle, which is 1. So it's 2a squared equals 1. A squared equals 1/2. A equals the square root of 2 over 2. And we get to this point here. So that means if we wanted to graph out this point here, it would be root 2 over 2, root 2 over 2. But this is where it gets interesting because this ties back into the trigonometric ratios we were looking at before. Because remember, if we're looking at sine, if we go back to the sine slide here, sine is this one. Sine is opposite over hypotenuse. So it's this one over this one. So if we go back and take a look at this now, if we compare those two sides, then we're going to be looking at, make sure I'm on the right thing here. We're going to be looking at this side divided by the hypotenuse side. But our hypotenuse is just 1. So in other words here, the sine is literally just this height. It is the y point. It is the y-axis point. Sine doesn't just tell you the ratio, it literally tells you how high this triangle goes. And in the same vein, cosine is adjacent over hypotenuse. So cosine is this side over 1. And divided by 1 just means it's this side again. So cosine literally gives you the horizontal. And last but not least, we have tangent. Now, tangent doesn't actually give you the side length. We already know the side length. It's 1. However, tangent is the opposite over the adjacent, which, if you remember all the way back when you were in high school, this is like the rise over the run. It's the y over the x. What tangent tells you is the slope. The tangent here of this angle is 1. It is this divided by this. And as you can see, this triangle does have a slope of 1. It's a positive slope, and it's perfectly passing through the line of symmetry on the diagonal here. Now, there's other triangles you can get with this too. So the next common ones we look at are what happens if we have 30 degrees. So with looking at like 30 degrees and 60 degrees, what we can do with that, and this is kind of interesting proof here. As you can see, like this here, or let me do this on a different triangle. That way you guys can actually see this a little bit better here. There we go, let's clean it up. Okay. So one way we can do this is if we make this line here, and this is 60 degrees, and that means this is 30 degrees. You can reflect this side over to the other side as well. Means this is also 30 degrees. This is 60 degrees. And if we connect these, now we have an equilateral triangle right here in the middle. And if all of the sides are 60, if all of these sides are 60, or all of these angles are 60, and the sides are all 1, that means this whole side is 1. And we can cut that in half. Each of these sides are half. Which now means that if we were to do the same thing we did before with the cosine and the sine, remember the cosine is just the the cosine is the x-axis here. This distance is exactly 1/2. And this distance we can also find. So if we're looking now at our 60-degree triangle here, we're looking at these 3 sides. 1, 1/2, and this mystery 1 over here. And once again, we can use algebra to solve this mystery, going back to our Pythagorean theorem. A squared plus b squared equals c squared, which of course means that 1/2 squared plus b squared, should be in parentheses, equals 1 squared, which means that we have 1/4 plus b squared equals 1, and therefore b is equal to 1 minus 1/4 square rooted, which equals the square root of 3 over 2. So this side is the square root of 3 over 2. And once again, we have this distance. This point would then be 1/2 root 3 over 2. And this is like, now looking at these ratios, we can find these very common angles like 60 degrees, 30 degrees, 45 degrees, all using the unit circle. And while the unit circle this is 1, and not all circles are 1, all you have to do is take these numbers and multiply with whatever the radius of your circle is to figure out the new side. It's looking at, like, again, the relationship between the sides. Okay, and then one last part that you can do with this is if we take these functions and we graph them out. If you look at the circle and you graph out, like, what is the height? So, like, for example, if we wanted to look at sine, let me pick up my sine color here. So we would start out at this angle and it would be like a really big number and would slowly get smaller and smaller and smaller. Oops, I went all the way past. But this width, as you can see, gets smaller and smaller as we go up the circle, all the way until it becomes negative and starts going around the other way as we are measuring this angle. And we can graph this out. We can graph this out onto a plane, an XY plane like this. And what you will see is that at pi over 2, or sorry, that was cosine, not sine. My bad. What we'll see is that we can start with a big width and going down all the way until we hit -1. We go back up. Oh, sorry, this is 0 here. And then we keep going all the way around. And this would be cosine. We could do the same thing for sine. Sine is looking at the height at every single point. So that's my like teal marker here. So as we begin, we would have like a triangle here. Let me get back to this. Whoops. Over here, like if we're looking at these heights, you can see the height of these triangles is increasing slowly but surely, all the way until we get to like nearly vertical. And then we finally do hit vertical, and that would be 1. Sine is measuring the y-axis. So if we graph that out, we would start at 0, get to 1, then turn negative. And we would have a graph like this, and this would be y is sine x. And lastly, looking at tangent. Tangent is measuring the slope of the lines now. So if I'm looking at the slope of each of these lines, our slope starts at 0, And as we keep going around the circle, the slope gets bigger and bigger and bigger, steeper and steeper, until we finally hit completely vertical, which is not a slope at all. And then we have a really very negative slope. And then coming down this way, all the way until we reach 0 once more. So looking at our graph here, what this would mean for this graph is that we start with that 0 slope, and then we very quickly go up all the way until we go and there is no slope anymore. And then we have a very, very negative slope all the way until we hit there again. No, it would be a 0 at 2 pi. And we would keep going with this pattern. And this would be y equals tangent x. Wait, that's not right. I messed it up. It should be 0. It should be an asymptote at pi over 2, not pi. So the asymptote should be here. There's no slope here. Very negative, 0, going up. And there's no slope. 3 pi over 2. There we go. Okay, now that is a whole lot of math. So let's talk about where you use this stuff in the real world. So those squiggly wave functions that we just showed, those are actually used in, for instance, calculations of light, which we will talk about. I think Cave is talking about light later, but light is a wave function. And this is a sinusoidal pattern. Also, the orbit of the sun, the earth, the moon, all of these are orbit around the sun. All the planets' orbits are placed in the galaxy. These all create circles. Just like architecture, how do you make sure that things are stable? What happens when there's forces that are going straight up, to the side, or even diagonally if you have a diagonal force? How do these balance out? The design of a building, obviously, you have triangles in buildings all the time. How do we find these angles? How do we calculate the exact distances we need them to be? Also, sports, if you're throwing a projectile, you throw it. No, you don't throw it perfectly horizontally all the time or perfectly vertically. You throw it at an angle. And we can calculate exactly the vertical speed and the horizontal speed. We can calculate those velocity vectors to calculate exactly what angle you're going at, and we can calculate that projectile motion of where it will land. Also, things like navigation. If you have sonar, we didn't talk about polar coordinates in this lesson, but this would relate then to okay, if I want to find something, where is it? How far away is it? And at what angle do I need to go in order to get there? And even to the point of the atoms that make up our universe. Those also have not exact orbits, but they have orbitals. And you can use trigonometry even in there because anything that is moving at an angle is trigonometry. So yeah, trigonometry. I love it. I love this stuff. And I didn't complete a full unit circle with all of these, but it's just so satisfying. It's so satisfying to talk about this stuff because I love how this connects. The concepts you learn in algebra, in geometry, everything goes together. It's beautiful. And that's my presentation. Oh, thank you.
Toto. Yep.
Thank you, Toto. That was amazing.
Yeah.
Wow.
So now we are open for questions about trigonometry.
That was really loud. Wow.
Xander being extra. I do have a note that she is definitely right. I don't think I've ever had a physics class I've ever taken where I didn't need to know this.
Yeah, this is so applicable to everything. This is just a really little introduction. A lot of people probably already know about this stuff, but I just love it. I love teaching this stuff over and over.
Because it appears everywhere.
Mm-hmm.
Trying to do
And then
physics
getting a
without this is
recommendation of this guy solving geometry problems on YouTube. And goddamn, if you figure out one triangle in there, you can solve anything, right?
Yeah.
Because the triangles just tell you so much.
Mm-hmm.
Indeed.
Triangles are so useless. Or not useless, useful. Squares are kind of useless. They're just two
We
triangles.
use trig a surprising amount in bioinformatics, mostly just to represent like
Population, you mean? Or not exactly population.
to represent like functions that go up and down. I forget the term for it.
Where does
Okay.
trigonometry
like
affect
regular,
computers?
I
with
don't
like a regular
remember.
intervals.
Ooh.
My brain is crapping out, but like just like but for the sine wave, sort
Yeah.
of.
Yeah.
Yeah,
Sine
waves
waves,
and,
sine
like,
waves.
going up and down. Sinusoidal waves, yeah.
Mhm.
Someone asked, like, where does this have an effect on computers? I'm not the computer scientist in the group here, but I do know that, like, in vector graphics, like just drawing stuff on a computer, showing them in pixels, that obviously requires like calculations. We're using trigonometry. Yeah, sinusoidal.
So having worked on video games, I can actually answer this, and that is that pretty much all forms of rendering involve really like quite a lot of trigonometry.
Yeah, or like shadows and like light calculations, like your ray tracing graphics. Like, what do you think a ray is when they're talking about ray tracing? It's a diagonal line.
Yeah.
That's true.
On a similar note, in the game design field, I've actually used it for enemy AI applications in which they'd use trigonometric functions to calculate your velocity along X and Y axes and use that to be able to intercept you with a projectile or something like that.
Oh yeah, for sure. Because if you're like moving in an X, like obviously nowadays in like we're not in the Atari like age, like you can move in a diagonal direction, and depending on how you move, like obviously that's a diagonal, and then you can calculate the exact velocity you're having in each direction by breaking it down into triangle.
Yep.
Or like if you've ever been in like the test area of a video game, like in a fighting game, where like you calculate like where they'll land or where they'll be like juggled. All of that is also trig.
I actually have used it in a Mugen to make AI intercept you with like optimal anti-airs.
Oh my god!
If it works, it works.
Yeah.
Yeah, and you can also extrapolate this out into a unit sphere, where we now have it three-dimensional.
Yes,
which is
yes.
How you define like what way you're looking in a video game, or what direction something is moving.
Yeah, because then you have a triangle here and you have a triangle here, and it's like, okay, where are you on that triangle? It's so good.
Because unless you have a game that's based entirely on a grid, it's pretty good to be able to have an expression for where someone is looking and where they are going.
Yeah.
Otherwise,
I just hate it when people say like, oh my God, all that math I learned in high school is so useless. It's like, no, you just didn't learn to apply it. It's so,
I think they teach not necessarily the right math and in the wrong order. I think everyone should have to take statistics.
Right?
Yes.
Statistics when it's like actually important, because like
you're like, statistics is super important.
Patterns in real life. It's because
but instead they teach you calculus, which is not very useful for most people.
Yeah. Right.
Like,
because calculus is about like calculating really exact things, but real life is not always exact, which is why statistics is so useful.
Calculus is important if you're going to is immensely important if you're going to do any kind of engineering.
Yeah.
But most people will never use it. And they teach you that instead of statistics, which is useful all the time.
Oh yeah, speaking of statistics, that's trigonometry too, because your statistics lines are like literally
calculus is very important for the development of logics in the brain, the pathways of the neurons is very important, but we can use other subjects that we can use more in daily life.
Yeah.
Right.
And then like obviously this has applications to calculus stuff too. Like if you have a curved line that's not like a straight diagonal, you can break it down into small diagonal pieces. This is like derivative calculus.
And most people who will use calculus in later on in life We will not
Yeah.
remember everything from school, so we'll have to learn all over again.
Yeah.
Yeah.
But this is stuff like I just want people to appreciate this stuff, even if they're not a mathematician or
Yeah,
even if they're not
yeah.
in science. I just want them to like love
Because
math.
math is flipping cool.
It is
Yeah.
cool.
Math is
Okay.
amazing. I don't remember almost any formula of math, but I do recognize it is amazing.
Yeah,
Science.
but the logic of everything you retain.
Yes,
When
that's true.
you try to learn it again, you remember the logic of how things work.
That's true. That's true.
Alright.
Someone
Okay.
asked, what's going on with pi? Why can't we sort it out? Do we really need all those decimals? You really don't need all those decimals. Even a lot of scientists will just go to 3.14. But I guess I never explained what pi is because that was not part of this. But like if you're looking at pi, here, let me see if I can get a place where I can draw here. Nope. Okay, but if you're looking at pi, pi is just the relationship between the diameter of a circle and the circumference. So it's like, I'm on the wrong layer. Let's do this. So if you have a circle, like imagine you have a pizza, right? And you're just like, okay, well, if I have this pizza and it's like this long, like this wide, how much times bigger is the circumference or crust than the width of the pizza? And you can like literally do this next time you get a pizza, is you can literally like cut off the crust and then line them up here and see how many you get. Really, it's the other way around. It's like if you have this, how many times does it go around the circle? It goes around 1, 2, 3, and a little extra.
There's
And that little extra is
experiment.
0.14.
There's an experiment when they turn a coin in a circle, and the coin turn a little more depending on the frame you are observing.
That's true, of course.
Yeah.
Oh,
Yeah.
yeah. I
That's-
know the one you're
that's
talking about. That was a really bad
yeah.
SAT question about the frame of reference. With, like, putting a coin around. Yeah. But this is all pi is. It's just like, how many times can you fit the width of a circle around the circle? That's all.
Yeah.
Very nice. Very nice.
It's a
Alright.
rational number, but it's not like that's like special. There's a lot of rational numbers. Like square root of 2 is a rational too, and no one talks about that one.
There are
Rational just
tons
means
of
it can't be represented like in a fraction nicely. That's all. It's not very special. People are like, pi goes on forever. A lot of numbers go on forever. What do you mean?
Yeah. Usually we just, at least in my math classes, we always had to just leave them in terms of like, oh, the answer is 2 pi. The
Yeah,
answer is 5
exactly.
square root of
Just
2.
leave it like this. Who cares
Yeah.
about the decimal? Just leave it like that. You can calculate on your own if you want to.
That is infinitely more precise than any number of digits you could ever draw.
Yeah,
Exactly.
exactly.
Had a joke in the chat from Eggs again, explaining something to an American. And now imagine a burger, because he is from Finland. He says, explaining something to a European. Now imagine a pizza.
Maybe for Italians. I feel like for Europeans it would be like, imagine a croissant.
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 Imagine some lefse.
I'm trying to think what you could say to a Brazilian imagine. I don't know. We have so many food.
Cool. You have a lot of
A
food.
circular food though.
I don't know what empanadas are Brazilian.
Yeah, we'll just stay with pizza. We love pizza right over here. Yeah.
Yeah. Imagine
Wild
pizza.
non-food related guess. Imagine a football.
Oh yeah, that works.
Imagine a football.
Okay.
But yeah, that only works for non-Americans, huh? Because our footballs look like this. Okay,
Yeah.
I'm sorry. I'm
Oh,
going
yeah.
on too long here.